I want to do something new. Specifically, I want to try to learn more about numerical computing, high performance computing in Rust. And to do that, I'm going to go through this course or whatever you want to call it. And I'll leave a link in the description. It's from some kind of French university, I think. But it's about implementing some differential equation, some like a model of a chemical reaction or something like that in Rust and trying to make it as fast as possible. So we're going to be going through that and we'll see what we can learn. So there is already a repository and you can like run the code using some kind of container and whatever, but we'll build it from scratch. Now in the beginning, it's kind of assuming you don't know anything about Rust at all. So we're probably going to skip that. But there is some setup, I think, like setting up a command line interface and other things like that that we will be going through. But anyway, we won't be reading the book from start to finish. All right, let's get started. To begin with, I think I will just make a new crate, and we're not. Maybe we'll later on upgrade to a workspace if we're gonna have, like, if we want to do split the compilation up into multiple steps. But for now, let's just do a single one. All right, so when we do this kind of numerical computing, we want to have a way to check whether what we're doing actually increases the performance of the algorithm. So to do that, we're going to add some crates to help us with that. But first, let us write some small test functions that we can kind of like use to check that our setup is correct. So for example, this one, basically we're going to say, we are going to say, I think we need to iter that, and then we can zip it with B, and then map, and we should get A and B. So let's call them X and Y, and let's do X plus Y, and sum that. Sorry, not plus, it should be multiply. And this is actually incorrect, it should be wrapped like that. All right, so that's one thing. And another thing, this thing called Hadamard products, we can do like this. And that is actually going to return a new thing. And that new thing is almost the same, except we don't actually sum it, we only do like this. Okay, so let's make some test examples. So 1, 2, 3, whatever. And B is, let's say 10, 20, 30. And then we have, let's say the dot is the dot product of A and B. And the Hadamard product is here. And let's go ahead and debug print those guys. All right, and let's try to cargo run it. And of course it did not work. Expected this one. Fair enough, so we have to say as slice. As slice. And here I actually also accidentally put A twice, but that's fine. Fix that now. And these are interpreted as integers, which is fine. So we just fix that like this. All right, now it should work. We can run it and we get that product is 140 and here's the Hadamard product. So that looks correct to me. So what we'll be doing now is adding this criterion crate, which lets us run benchmarks. Let's go ahead and try that. Cargo add, and it's a dev dependency, criterion. So there we go, we have that. Now if we look here, we have it in here, and we need to add this bench section. Let's try that. Here we go. And we'll just call it benchmark. I think we have to make a file here, a folder called benches. And is that not correct? First, you need to create benches directory and create a source file here, name however you like with a .rs extension. Right, so let's just call it benchmark. And what do we put in there? We put in this stuff. So let's do that. And here we're gonna say, okay, just benchmark the dot product. And I think somehow this stuff is not included, but okay. Let me zoom out a bit. Anyway, dot product, and we want to use create dot product, but that is probably not exported. So maybe this had to be library, but here we are. How do we do that? Right, I think we have to say use Gray Scott and dot product. That didn't work either. All right, I think I figured out. I refactored it so we have now it's a library, and then we can actually import it here. And what we're going to do is some number of times we're going to run a function here, and that function is going to be, let's see, let's generate some vectors like whatever, and like let's make it 1,000 long, and b is the same, but like some other number, whatever. And then we're going to run the dot product function on that. Like this, and actually we don't care about the result. Great, I think this is more or less correct. So now we can run cargo bench, and it's going to compile a bunch of stuff that the criterion thing depends on. Now you can see it says it's warming up. So it's trying to estimate how many iterations it can use for testing, and now you see it's finished. So the time it took was, the fastest one was 473 nanoseconds, the slowest one was 475, and the average is 474. And then it gives some statistics and stuff. And this should say somewhere, I think, no, it says 100 measurements. I'm not sure. But anyway, you can see here that it's actually quite fast. I think, well, it's only 1,000 numbers, so I don't know. Now we have this, and we can, when we go ahead and implement other functions like this one, maybe, you know, we did some kind of mistake and we actually like run it twice or something, then we can go ahead and add another benchmark. And we can see if our changes have made any difference. Like that, right? Now I had an underscore, it's fine. Like this. Let's try to benchmark that. And 2, I suppose. So now it's running the benchmark of both. And the dot product is the same. We didn't really change that function. So normally you would see if there's a significant change here. But you can see that our second implementation is actually quite a bit slower. It's not twice the time, which is actually kind of interesting. It probably means that we have done something wrong in the benchmark. What if we pull these out here? Pull them out. And like this, no? Remove the extra argument. What is it talking about? All right, so now I changed it so these are created out here, and then it's iterating this thing a bunch of times, and still now bizarrely the second one is faster. I can't really explain that, but I guess you can see that we can actually test how fast our functions are. I'm going to delete this one again. Can I format it now? I can format it. All right, now we'll try our first foray into some high performance stuff. We'll try to do some single instruction, multiple data. So like vector instructions where the CPU can do multiple arithmetic operations at the same time. And I do think we're going to need to use Nightly for that, if I recall correctly. But first of all, let's try to get things set up. So let's see here. This one should be on the top. And file not included module tree. Right, so whatever. Let's go ahead and say rustop default Nightly. And let's let that update. Now we have Nightly. And it should soon understand that we are using Nightly. Whatever. So we need the multi-version crate. There we go. Should be doing that. Let's put this on top. And file not included module tree. It's not correct. But whatever. Okay, so how do you do CMD? You specify some targets here. I think my CPU is x86-64, and then there's some instruction sets here. SIMD instruction sets. Anyway, let's see here. Let's just do it like this. There's some problem with the proc macro. I'm not gonna deal with that right now. Let's just see if we can get this to work. So what does it do? First, it gets the CMD width. Then you turn the vector into a CMD thing. And this works for slice. That's nice. So here, like this would basically be like 3 or something, and then you add up 3 numbers at a time. And let's try to implement the dot product since we've been working with that. So what we can do here is, well, let's keep this one as a reference. Let's go ahead and add CMD dot product, which obviously now it's going to take 2 things. Get the selected target, and these guys should probably call like X and Y, X, X, and here Y. that. And now let's say CMD multiply. Basically want, I'm not sure what peel is. Body and tail. I guess that's like the front and the back. If there's something that doesn't like fit into the CMD thing. All right, so we have this guy and we can turn it into an iter and then we can zip it with Y and we can map that. X and Y should now be some kind of CMD thing. And I think we can say X times Y. And finally, let's sum it like that. Is that how they do it here? They sum into some awful thing. So we'll do that too. We'll do that too. Okay. So let's get rid of some of these compile errors. Okay, so it's this into iter call is equivalent to iter. Okay, so I'm getting some kind of corrections from my editor that the code is wrong. To be fair, the code is kind of old, but all right. So what we want to do now is, let's say the rest. We need the X peel. We need to iterate it. We need to zip it with Y. And then we need to chain that with this guy zipped with the tail of Y. Okay, so we have that. Then we want to map that stuff. X and Y again. X times Y. And then just sum it. Right, and then we want to do this thing. Let's call it scalar dot cmd dot and dot. So we should really test that it actually do they specify the type here? They do. So we'll specify the type as well. We should really test that like this CMD implementation matches the sequential one, but we're not really going to do that now. Let's just see if we can get the benchmark to work. So we'll add another one. And actually what we should maybe do is do something like for size in 1, 8, 64, 512, 2048, and let's see, 4000 something, 4096, and then we need a really large number, something like this. It's probably too much. What's that? Like 1 million, 2 million. I think this number is good. Let's go with that. Okay, so for each of the sizes, we're going to create a benchmark, separate benchmark. And we'll have like, we'll put the size in here, I guess, like that. And it needs a string, so let's do this. Great. This one is going to be cmd.product, and it will also take a size and like that. So what we're going to do is actually put the size in here, and this one is going to be cmd.product, which we will need to import. Go. And it's private, but that's a mistake. Let's go back here. So now we have them. Let's get out Python and let's try to benchmark that stuff. All right, so all the benchmarks ran. It took a little bit, but probably we shouldn't have benchmarked that are this small. But I want to do it to illustrate a point, which is that, as you can see here, the dot product for one number the sequential one took 1 nanosecond, and the one using parallel execution took 3 nanoseconds, so it was slower. And if we have 8, it takes 2.5 nanoseconds with the sequential one and 4.8 with the parallel one. And it's actually only when we reach a certain like problem size that it starts to matter. So here at 68, you can see 13 nanoseconds with the sequential one and 6.9 nanoseconds with the parallel one. So, and that's kind of a common theme, that it doesn't really make sense to parallelize unless you have a sufficient number of things to process, because there's always a little bit of overhead that you have to pay, basically setting up the parallelism framework takes some time, and there's just no way around that. But for example, here on this large problem, you can see it's a huge time saver, like a factor of 8. And it's probably going to be around 8 or something, usually. So here is the, let's look at the final example, which has like 4 million, 1.7 milliseconds versus 7 microseconds, which is 0.7, I think. Does that make sense? Microsecond, yeah, I think it's 0.7 microseconds. So it's actually not so much faster. It's not as much faster than I would have thought, but okay, whatever. So that is CMD. Now we have a basic framework for running CMD things. And let's see what the next thing is. All right, the next thing we're going to be looking at is instruction level parallelism. So CMD is a special type of instruction that can operate on multiple data at the same time. Instruction level parallelism is a way for the CPU to actually run multiple instructions at the same time. And I think the CPU kind of figures it out on its own. If it sees that it can run things in parallel, it does it, or like it usually tries to do that. And the way you can make it clear to the compiler that it can do it is to have something like this. Here I have 3 operations. They're completely independent of each other, clearly. So it can actually run those at the exact same time without changing the program. So it will try to do that. And you see here there's a to-do like add CMD here, so you can even have ILP, instruction level parallelism, on top of CMD instructions. So it will run multiple multi-data instructions at the same time. But anyway, instead of doing this by hand, there's this crate made by the guy who made this course. So let's try to use that. So we should probably add that. It's called iterator ILP. And now we have that. Amazing. So let's go ahead and say, let's call it ILP.product. And we need the same, sorry, this is actually just an F34. We need the same signature. And then it's quite simple. You just do some ILP. Something like that. So actually what we want to do is we want to say, okay, give me an iter, zip it with y, map that stuff as we, so some problems with my Rust analyzer, great. But we do this, and then we can say some ILP, which we probably need to import something here. So iterator ILP, this guy, the interface trait. And it should be summed to an F32. And you also need to give it like how many things should it try to do in parallel. Let's say it should do 8. Let's say it should do 8. And then we can go and add it to our benchmark. So we'll do that here. like this ILP and ILP. Don't want to do all of these benchmarks. Let's remove some of them like this. So we have a small, like in the world of numerical computing, a small and let's say medium, and then this is like somewhere between regular and large, I think. So let's run the benchmark again, and I will see you when it's done. All right, the benchmark is finished. Let's take a look at the results. So here we are. The small problem, we see that the sequential one is the slowest, then is the ILP one, and then is the SIMD one. Let's take a look at the next one, and it is the same story. And then here in the large one, we have 1.7 milliseconds for the dot product. The sequential one, sorry, the ILP one, 1.3 milliseconds, and the SIMD one, 0.7 milliseconds. So at all scales of the problems, SIMD, pure SIMD is faster than ILP, and the sequential one is the slowest. So that makes sense, I think. So what we can try now is to combine these two. So let's say ILP SIMD dot product, and we need that stuff. Do like this. So we're going to copy paste this stuff. And what we're going to say here is just in this one, it's actually going to be an ILP sum. So that's actually quite easy. Let's do 8. I mean, this is something that maybe should be tuned, but whatever. And this one, since it's generally, I mean, I don't know, maybe we shouldn't have it here because typically like the leftover parts won't be that large. So I'm actually going, this is something you should test probably, but I'm actually going to say that we don't want it here. All right, and this should be a function. This should be labeled with a function. For some reason, we need this stuff. Okay. And this one, you can't do it on a map. Or no, that cannot be true because we had it here. So it's not implemented for this type, it seems. The SIMD type. Interesting. Let me check that out. Okay, there may be a way to do it like this. Like with the fold thingy. So can I do that? Fold ILP. That one I can do. Does it also give me? It does give me some. So I don't know. Let's try this one. And how does it work? Give it a type. So we're gonna give it just 8, and then you give it something to initialize. Do we have this struct? We do have this struct, and it's going to be zeros, sure. And then we have to take the accumulator and the element, and that is just going to be accumulator plus element. Maybe we do, is it just like that? No, and it's SIMD thingies. And finally, how do we merge the accumulators? It's also just, everything is just added together. So does that work? And I should have this one. Just like that. Okay. Great stuff. So what actually is this thing now? It is a SIMD, all right. So you have to kind of do it like that. All right. I mean, it compiles and we have ILP and we have SIMD stuff. So what does it do actually? So first, we use SIMD to multiply all the elements together. And then we use a CMD way to add things together. All right. It is what it is, and it isn't what it isn't. So here we go. IP and SIMD. ILP and SIMD. Let us run the benchmark, and I'll see you in a bit. All right, so here we are. It's done. Let's take a look. And this one got a little bit slower. I guess I was tired. So if we look at just the SIMD, which was the fastest on this one, it was 20 nanoseconds. If we use ILP with CMD, we get 26. So it's a little bit slower. Let's jump to the largest problem. 770 microseconds, and if we do just SIMD, it's 741 microseconds. So bizarrely, it's kind of not helping us at all. Maybe, who knows why? What kind of numbers are they using? Because that can sometimes mean a lot. It's using 2 here. So why don't we do that? And this one we can also do some ILP. Let's try with 2, and let's run the benchmark again. All right, here we are. Let's see. Now it's actually slower. It is actually slower than before. All right, but at least it's something we can try now to play with in principle. But let's leave it here. Let's leave the instructional parallelism here. So final thing I think we're going to do in this video is to take a look at thread level parallelism. So we have been trying to use a single CPU efficiently. Now let's try to use multiple CPUs. So we're going to use Rayon, which is kind of like a super nice way to do thread level parallelism. And you can prelude like that. And let's go ahead and take a simple version, because usually it's very simple. We can just put PAR-ITER here, if I'm not mistaken. And does this compile? So set is something that can be turned into parallel iterator, which this one can. We just apply a map, and then we do a sum. So I think the only thing we changed was to put par here, parallel, and it will parallelize over threads. So that is quite something. So let's go ahead and add that to the benchmarks. And we'll just say rayon.product. And we will add that here. Rayon. All right, let's try to benchmark that, and I will meet you when it's done. All right, here we go. So the Rayon one, even though we didn't do anything special, like sometimes you want to say don't parallelize over everything, like create some chunks and whatnot, but we didn't do anything special. We just let it handle it itself, and we actually got the fastest version yet, 500 microseconds on the last problem versus 738 microseconds on with CMD. And I think let's look at the other ones. Rayon on this one, 200 microseconds. It's a bit slower than this one. So it's only on the very large problems where thread level parallelism beats the other ones. And probably if you combine them in a nice way, that will be the fastest. Thread level plus SIMD. But we're not going to be doing that in this video. I think we're going to call it here. The next thing we want to do is to add this ND array, which is like a super nice crate for working with numerical data. It has a lot of nice things, and we don't have to do so much manual checking of compatible sizes and things like that. If we were to that we would have to do if we were to use the raw vectors. So we're going to be doing that, and then we'll start looking at this gray Scott problem. So until next time, bye bye.